probability density functions are to continuous random variables as probability mass functions are to the discrete random variable. Oh, that's a mouthful, right? The idea here is that the continuous random variable, which is now a real number that could take on any value, even though it might be between specific ranges, it might have an infinite number of decimal places, right? And probability density functions are what describe the relative frequency of that variable taking on something in a range rather than a discrete specific number. Oh, wait a minute, that's still kind of confusing. Hey, let's illustrate this by going back to our traffic gap problem, our pedestrian crossing one. And let's look at that discrete version of the time axis, where we said that the times in between vehicles came at us in one of 5 different sets of values: 3, 6, 9, 12, and 15 seconds. We didn't talk about why the engineer chose to discretize in that particular fashion and why they felt that, for instance, there were going to be no gaps larger than or smaller than the range that you see there. We just took it on faith that that somehow was reasonable, and we went from there. Right? And we created the probability mass function that was in the ratio of 1 to 2 to 3 as we went from 3 to 6 to 9 to 12 and to 15 seconds. Right? And that was really 3 ninths, 2 ninths, and 1 ninth. Right? Add up all those probability masses, and they had to equal 1 for 100%. We had no other possibilities. We couldn't have a time gap of 4.5 seconds in between or 6.82. Well, okay, we could, but what we did was we said, well, that we'll lump it to the nearest one of these discrete versions, so that we lumped all the probability right here, and it became a mass. So therefore, we could just add those up, and total had to be exactly equal to 1. Well, now we're interested in broadening this out so that we can look at this in a somewhat more realistic fashion and let time be continuous. Notice a lot of people, when they go from discrete to continuous, will go from a capital random variable to a lowercase. And, you know, it's 6 of one, half dozen of another. And now, although we'll still have maybe some important numbers here at 3, 6, 9, 12, and 15, we're going to think about this in a little bit more broader view. And that is, let's think about this in terms of, well, are there any maximum and minimum values? And is there anything else that's characteristic about this probability mass function that we want to preserve? And certainly one of them would be that we want to keep the center of mass at the same place. That would be at 9 seconds. There's your mean. Right? We also note that, gee, there's a linear progression here, and if we extend the lines, we see 2 different things happening. One, that there's a lower bound at 0, actually physically makes sense, and then the upper bound is at 18. And maybe we think that time gaps between cars could actually be larger than 18, but for whatever reason we think it has such a low likelihood that we're willing to discard that as anything sort of significant. Right, so there's our min and max values that we'll take from what we implicitly had in the probability mass or discrete version of things. Right? And we want to preserve the symmetry that we see here in the top. It's symmetric about 9, so we want to do the same thing, and it's maybe reasonable to think, well, okay, then we'll just have a linear variation in both sides, going down to the min and the max. This line that I just drew is going to represent our probability density function for our random variable. Right now I've gone back to, hey, here's my capital T, and then inside the functional description I have a lowercase, and that's more conventional. Right? The question then becomes, well, what should the height of this triangle be? right? And we're going to get there by recognizing some of the properties that we must have here. Right? In both cases, a discrete and the continuous world, right? And let's write that down. We've got the continuous model down below. We have the discrete model up above. In both cases, our probability values, or the values represented, had to be greater than 0. We didn't write that down up here, but that's each one of these probability masses has to be larger than 0. It can't have negative probability. Likewise, our probability density function has to be greater than or equal to 0 as well, right? So implicitly here, what I've just told you is a PDF has this symbol of a lowercase f, and then you've got your argument sitting here, which in our case is t. And some people will put then that capital T to indicate the random variable of interest. Other people won't. You'll see that actually in the textbook that they don't, unless it becomes important for some reason, communication-wise. Right? So all these probability density values have to be greater than or equal to 0. We've already preserved symmetry. We'll talk about how we knew that we were really going to get that from a mathematical standpoint, but just a geographic or a geometric standpoint, we can tell, hey, center of mass is going to be right here at t equal to 9. And the one property we haven't used is, well, the total probability has to equal 1. Right? Well, there's two ways we could really approach this. One of them is the nice esoteric approach of, hey, let's take a little range that is dt. Yeah, you know where we're headed, don't you? And there's our area. And so if we looked at the integral over all of our possible time values, well, ft of t, right, that's the height of our rectangle, times dt, sum up all of that, and we end up with 1. Right? That really, this is a probability mass in terms of area. That's why I said before that the likelihood for a continuous variable that it takes on one specific value is 0, because there's no range there. But if we talk about a dt range or anything that's now incremental, I can now talk about a real probability number. So probability density has units right, of probability divided by, well, whatever our units are of our independent variable, right? So in this case, it's going to be probability, let's just call it width, right? And it's the variable was seconds in our case, so it would be probability divided by seconds for that particular density. Multiply back by the width by seconds, and you get, of course, probability. Add them all up, and you get back to 1. Right, that's key. Notice that for our problem here, rather than try to come up with the actual mathematical function for each one of those segments, why don't we just recognize that that's the area of a triangle? And so in this example, we'd have 1/2 times the base of 18 seconds would equal the height. And so our height would equal then 1/9 seconds. The seconds are in the denominator there. Okay, so there's your equivalent height. Now if you really want to write the mathematical equation for the straight line for both segments, go for it. Be my guest. We'll get to, in a second or so, in the next learning sequence, we'll talk about how you find the mean and the variance for this continuous random variable. But here, the key things are to note that we've got several properties that are pretty important. One of which is the probability density is always greater than 0, that the sum or the area under the density function, sum of all the probability density times a little width, has to be equal to 1, and we can use that to find some parameters here, either a nice simple brute force way or otherwise do the elegant math inside the integration symbol. And implicitly I've talked about, well, if I want to find the probability of a continuous variable being in a region, it's really just area under the affected portion in the curve. What that would look like in terms of a more formal statement is that the probability that our random variable is between two different values, and notice I've written that with the less than or equal sign, but it really, because of the zero chance to be a specific value, we can only talk about regions. It wouldn't matter if we said less than or equals if we said less than in this case. And that's just going to be the integral from a to b of ft of t dt. So up here in our probability density function curve, let's say it was between 12 and 15, it would be that area right there. And that's the third property that you'll see listed in the textbook.